Welcome to the annual Hassan Distinguished Lecture in Aerospace Engineering at NC State University. I'm Srinath Ikad. I'm the department head for Mechanical and Aerospace Engineering here at NC State. So welcome to the annual lecture, and we are excited today. We have a great speaker and a great topic. I think it's timely. But before we get started, I want to introduce another person uh, who will say a few words. Dr. Hassan, uh, Hassan, who the lecturer is named, was a longtime faculty member in our department. He has a very strong impact on our aerospace engineering program. He was here for 56 years as a faculty member. Unfortunately, a couple of years back, he passed away. But he was a presence at all these lectures. And in fact, the last one, 2019, he was very much here. And he's also contributed a lot to many aspects of NASA's missions over the years. He has a tremendous number of students who are working out there, who all uh, indicate their success directly to being his students. So that's the impact he has had. And when he retired, he decided to create, about the time he was retiring, he decided to create the annual lecture. And he also has scholarships for aerospace students. And as of this year, past year, we have now a new Hassan Distinguished Professor, endowed Distinguished Professor, that's going to be somebody we are looking for to hire in fall of 2022. So a lot of impact by Dr. Hassan, but another Hassan also has had a lot of impact. So I'm going to introduce Basil, who is Dr. Hassan's son, but also a three-time alumni of our department, and currently our AIAA president, and also a very strong supporter of the department and the college. So Basil.
All right, good morning, everyone. I want to thank everybody for joining us today for this distinguished lecture to commemorate my father. And I'm thankful for all of you who decided to attend in person, as well as all of you who have joined online, so thank you. As Srinath mentioned, this lecture got started in 2015, and there were several folks in the department who were instrumental in making this happen. So I want to thank Mohammed Zikri, Rich Gould, Jack Edwards, Srinath Ikad, and Mike Walsh, who were helped put this together. You know, as Srinath mentioned, my father showed up in 1962, and he was very instrumental in starting the aerospace program here. Um, he he really loved this department. He was a mainstay until he retired, and so I think it's 56 or 57 years that he was here. He was devoted to his research. He was devoted to his students, and you know, part of this lecture is his legacy for not only the current students, the current faculty, but as well as the rest of the community. A few of the students that he has taught or advised are in the audience or probably listening, so thank you for joining. Another way that he wanted to make sure his legacy was felt by endowing a couple of scholarships, one through the NCSU Foundation and one through the AIAA Foundation. And I believe a few of those students who have received those awards are here today. So I am actually thrilled today to introduce longtime friend and colleague Bobby Braun to give today's lecture. Bobby's formal biography is in the handout you got, but we first met actually in the early 80s or late 80s at NASA Langley Research Center when we were both students. And Bobby was working for a former NCSU professor and longtime NASA division chief named Jerry Wahlberg, working and designing tools and capabilities as well as missions that were going to support future Mars missions and future planetary missions. We both shared an office and a trailer at NASA Langley and got to know each other pretty well. Bobby got his bachelor's degree at Penn State University, and then he was working on his master's degree through George Washington University through a joint program that they had with NASA Langley. I will say that I think those of you who are in the audience Bobby should be considered a role model for you. He's had the opportunity to impact a lot of areas of the NASA vision for space, policy, very influential in policy. He spent time not only at NASA Langley as a researcher, but also as a professor at Georgia Tech, a dean of engineering at University of Colorado. He took a stint at NASA as the chief technologist, and right now he is doing probably a dream job for most people in aerospace engineering, and that is supporting the planetary sciences mission at JPL. And so, without further ado, I will get off the stage and turn it over to our speaker today, Bobby Braun.
Wow. Thank you for that wonderful introduction, Basil. Appreciate it. I hope you're doing well. It's good to see everybody today. This is my first visit to a university in a number of years, and something that I've missed greatly. I love going to university campuses and meeting with students and talking, frankly, about this topic that I love and which has been a passion of mine for most of my life and the focus of my professional career. Before I get started, I just want to say what an honor it is to have been selected to give this seminar. Professor Hassan was a role model for me, and the faculty at NC State at that time were role models for a large group of graduate students who were all my friends, my colleagues. Many of them are at NASA Langley or Sandia or NASA Ames today. And this group of students, which was centered at NC State, it's probably on the order of 20 or 30 graduate students that are all roughly my age. So in the 80s, we were all, 20-something, and are now in their 50s and have contributed to really grow the aerothermodynamics community at NASA, in the Air Force, and for our country, basically. And NC State should be very proud of that aerothermodynamics focus that it grew over over those many decades, because the contributions of that group of faculty and through that faculty group of students, who I was only tangentially, a part of. I went to a different university, and I was a friend, basically, for these students. I didn't work in that field directly, but that group has really made contributions to our country, and it's something that the university should be proud of. So anyway, when I got the call, if I was interested in doing this, I just jumped at the chance because, frankly, it's just a real honor to be here with you today. Now, I'm going to talk about my love and one of my loves and one of my interests over my life, which is planetary exploration. So you heard in my bio, I've worked in a number of places. I started my career at NASA Langley Research Center, in southeastern Virginia. I've been at Georgia Tech, at the University of Colorado Boulder, and now I'm affiliated with Caltech. I'm on the faculty there, and I'm on the leadership team at the Jet Propulsion Laboratory. And even though I've moved around to a number of different organizations, the one constant in my career has been contributions to our nation's planetary science missions, visions of planetary exploration, where we humans send our emissaries in the form of robots out to the planets to explore for us. And one day, of course, humans will travel themselves. I started my career thinking and dreaming about human exploration, humans on Mars. In fact, when Basil met me in the late 80s, that's what I was working on with Jerry Wahlberg, who ended up starting the Mars Mission Research Center here at NC State. And I worked in that area for a number of years, but it was really the robotic missions that were advancing quickly, and so that was where I was able to contribute. And I've been a part now of 7 different landings on Mars and several missions to other planets as well. And so what I want to talk to you about today is not the past, although I'm definitely going to touch on perseverance and ingenuity, because what happened during this pandemic year, being able to land on Mars and still explore. I mean, frankly, I think it helped the whole country to be able to see what we can still do when we work together, even in difficult times. So I'll talk about perseverance and ingenuity, but I also want to like feed forward and talk about some of the missions that you'll be hearing about over the next 10 years, because we're working on them now in the laboratories at the Jet Propulsion Laboratory, at places like Lockheed Martin, or at NASA centers like Langley and Ames. People all around the country are working on these things now. Now, I'd be remiss if I didn't start with a little bit of history. Of course, the Jet Propulsion Laboratory has been around for a number of years and has focused on robotic exploration since we've sent satellites into space with Explorer 1. The payload for Explorer 1, the first US satellite, came from what became the Jet Propulsion Laboratory. But JPL has had a central role in a number of firsts over the years, including the first robotic landing from the US on the moon in 1966. There's a 1966 graduate here somewhere. There we are. Is that you? 65. Sorry. You just barely predated this one, Doug. Viking, the first US landing on another planet. There were 2 Viking landers, and they landed on Mars in 76 and 77. Actually, they were led out of the Langley Research Center, and when I was a kid, about 11 years old, I was brought to the Goddard Space Flight Center by a neighbor, and I got to watch on a big screen the landing. Well, it was very different than it is now, because it took like hours for the image to show up on the screen bit by bit. But I watched that first image come from the Viking 1 lander in 1976. And I was fascinated then by the engineers and scientists who had made that possible, how they jumped up and down and, tried to high five each other, like only engineers can. And just, their general excitement at having done this remarkable feat that led to all kinds of science, led to understanding about Mars, and led to greater understanding, frankly, of the Earth. It's interesting, but the very next lander after that was Mars Pathfinder, which landed in 1997, and I was on that team 20 years later. But in the intervening years, we had Voyager, Voyager 1, Voyager 2, which have now left the solar system and are interstellar explorers that we're still communicating with. Space is a big place, right? And these missions, which launched in 1977, are still going strong, right? It's remarkable when you think about it. And I mentioned Mars Pathfinder, but we also had Mars Global Surveyor that launched in 96 and 97. And since that time, the US has had a continuous presence on Mars. It's interesting, we've had a continuous human presence in low Earth orbit since about 2001. And so in human exploration, we talk about 20 straight years of continuous human presence in space, not the same person, obviously, but in a handoff sense, continuous humans in space. The Mars programs had continuous presence on Mars even longer than that. And that is something I think that our country and engineers and scientists from universities like NC State can take great pride in. Now today, in my job as the Director for Planetary Science at JPL, I'm responsible for all the robotic missions that go out into the solar system to explore. So not the spacecraft at the Earth or those that go to the sun, but all the planets, the moons, the asteroids, comets, all of that. And it is just a fascinating job because I get to work with some of the best scientists in the world. We get to dream about sending probes to places that you really it's hard to even imagine some of these environments that our spacecraft are operating in and sending us information back on. And we get to make these machines that do first-of-a-kind, one-of-a-kind things, like the Perseverance rover that we'll talk a little bit about today that's exploring Mars right now, or the idea of flying a helicopter not just on Mars, but on Titan, which the Applied Physics Lab is working on this. It's a moon of Saturn, or exploring the oceans beneath the ice-encrusted world of Europa, a moon of Jupiter, right? And while we're working on all these missions, we're operating a whole series of spacecraft that previously, in decades before us, were dreamed about, built, launched, and are now in operations at Mars, at Jupiter, and elsewhere. So today at JPL, we have these missions over here to my right that are in operations, and we have these missions to my left that we're operating, that are in development today. So that we're building and getting ready to launch. And I'm going to focus largely on Perseverance, which launched in 2020 and landed in 2021 in the midst of our global pandemic. And then I'll talk a little bit about these future missions, and in particular, Mars Sample Return, which has been a focus of mine for several decades. So another way to think about this is we have these missions in operations. This is just a list of them. Missions in operations with their launch date, and a whole series of missions in development at JPL. And I'm not going to go through every one of these, but what I want you to realize is that today, as we sit here, there are engineers and scientists all over our country that are already building spacecraft that you'll hear about in the coming years. In the next 3, 4, 5 years, these missions will launch. And for students that are here, I'll say these are things that you could be a part of. We need mechanical engineers. We need electrical engineers. We need aerospace engineers. We need all kinds of business and liberal arts and science majors as well in these programs. And so if you're interested in any of these missions, you can look them all up online. There's all publicly available information. But we've got missions to asteroids. We've got a whole suite of missions to the moon. These are all robotic missions. Suite of missions to the moon. Europa, I will talk a little bit more about. We've got some Mars missions in here. And towards the bottom, at the end of this decade, we've got a whole series of missions that the United States is going to be sending to Venus, a very different planet, right, than Mars. In fact, what we know about the inner solar system, the rocky planets, from Mercury out through Mars, is that at one point in time, these worlds, 3.5 to 4 billion years ago, were all somewhat similar. They were all warm, somewhat wet planets. And of course, they've diverged in their history greatly. Venus is very different than the Earth. Mars is very different than the Earth. And in some ways, Venus and Mars bookend the Earth. I'm very happy that we're all here on the Earth, by the way. While I study all the planets, I have to, accept the Earth. I have to admit that the Earth is still my favorite planet because it contains all the things we need to live and all the people that I love, frankly. When we study Mars or when we study Venus, what we're really doing is we're understanding how that world changed over time, but we're also understanding how the Earth changed over time. We can learn about the Earth's past on Mars because it hasn't had tectonic history, for instance, that has altered the crust like it has here on the Earth. So ancient history on the Earth has largely been wiped away. But that's not true when you study Mars. We can learn about our potential future with greenhouse gas runaway by studying Venus. And so NASA's interest in Venus is prevalent in our plans going forward. This just presents the same information on a timeline to give you a sense that we are continuously exploring the planets. And for good reason, right? I want the Earth to stay habitable. I like living here. I'm sure you do as well. And I want to learn about more and more about our world, our home, where we came from, where we may be going. And those are big questions that we can only address through planetary exploration. So let me focus in on Perseverance. The Perseverance mission, I should mention, people that worked on this, and there are literally thousands of people across the country who worked on this rover. You probably can't tell from the image, but this rover is the size of a car. Okay, it's nuclear powered. And on its arm here, it contains instruments that are roughly the size of one of the MER rovers, Spirit and Opportunity, that we sent to Mars back in the 2004 timeframe is when they landed. So you probably know that Spirit and Opportunity lived on Mars for quite a long time and explored a great deal of the Mars surface. But imagine that entire rover being placed on the tip of an arm that is now being manipulated autonomously and being driven, by the way, autonomously, largely autonomously, doing amazing science. That's what Perseverance was built to do over about a 7-year period here on the Earth. And that's what it was planned to launch a long time ago, planned to launch in 2020. But of course, that plan was put in place before there was the global pandemic. And so in March or so, when the pandemic was coming, we had a huge decision to make. Our launch window, which comes around once every 26 months, was opening in late June of 2020, and yet the world was shutting down. We were all being sent home. Now, when you're working on a project like this, there are certainly things that you can do from home. We've all learned that we can work from home and we can study from home and these kinds of things. But when you're building a spacecraft and you're putting it on top of a launch vehicle, the team has to get together, right? They have to get together in the clean room at JPL to test the hardware, and they have to get together in Florida, where the vehicle launched from, to get to put the hardware together, basically, and to make it work. And so JPL took extraordinary measures in that time frame to meet our launch date. And to be honest with you, there were days where I didn't think we were going to make it. And there were days where we thought, we're going to miss our launch window and have to wait 26 months and spend more money, by the way, to make this thing happen. But the team really buckled down. And it wasn't just JPL, it was United Launch Alliance, folks at the Kennedy Space Center, and we got this mission off in June of 2020, on time. We had a pretty quiescent cruise, pretty quiet cruise to Mars, and then on February 18th, 2021, we had our entry, descent, and landing. And that's been the focus of my work. That's something I started working on when I was at the NASA Langley Research Center. And that's the area that I mentioned I've been a part of 7 different landings. That's the area that I have contributed in, along with a number of other people around the world. And so those 7 minutes of terror, as they've been known to be called, was an extraordinary time in February of 2021. And it was the 18th. It was a day I'll never forget. And so I want to share with you a little bit about what that was like. Hopefully you were able to participate in this mission event from home during the pandemic.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So it's funny, I've probably watched that video 100 times, but it always gets me. And the reason it does is, I know all those people. And I know what they went through. Sorry, there you go. I know what they went through. And they're all heroes, frankly, every one of them. Every single one of those thousands of people that contributed to that moment. And what they sacrificed, or potentially what they risked, during the global pandemic to come to work every day and to make that happen. It was a scary time for everybody. The other reason it gets me, to be honest, is that, that's the role that I had on Mars Pathfinder back in 1997. And now when I look into that control room, it's a lot of my students or a lot of my younger colleagues that I've met over the years, and many of whom I've mentored in one way or another, that are actually in those same roles that I was in, 20 years ago. It certainly was a fantastic day for JPL, for our nation, for the world. I think it, you can see from, President of the United States was watching, right, live. He called the team shortly after we landed and gave us his personal congratulations. There have been all kinds of, congratulatory calls that have come in from around the world. President of France, there's a major instrument that comes from France, and the President of France called as well that same day. And you can see the way the newspapers reacted. Cities were lit in red in celebration. This is Pasadena Town Hall. You can see Cleveland there, New York City in the video. It was a remarkable accomplishment and one that I'll frankly always remember. But there's more to come. There's more to come. Before I leave Perseverance, let me just talk a little bit about it from a technology standpoint. So Perseverance was going to a place that frankly we couldn't have landed in just a few years previously. We didn't have the capability, and we certainly wouldn't have risked such a big system. So we've been sending probes to Mars for a while, but we tend to send them to places where we can land safely, right? If you want to explore, you've got to land. You get no science otherwise. But places where you can land safely tend not to be that scientifically interesting, right? Do you really want to do scientific exploration of a large parking lot? Probably not. It's going to look pretty homogeneous. What you really want to do is land, in a small crater, with a huge crater rim, with maybe a mountain in the middle and big boulders around. All those things are landing hazards. So what is shown on this image in the upper left there is a map that Perseverance carried with it as it descended to the surface. The red colored areas are danger areas, places we did not want to land. Now, I'm not saying that in every one of those red spots, it wasn't certain death, right, for the lander, but it was a high-risk place to land where we could have lost the lander. And so the goal was to go to this region and land in the bluer spaces, even though we had no idea precisely where we would be coming down. We knew we'd be somewhere in this frame, but we'd be all the way on the right or all the way on the left, the top, the bottom. That was unknown on the day that we were flying through the atmosphere where there's no coming back, right? Once we launched, we were going to land. We were going to hit Mars one way or the other. And so as the vehicle descended, you heard in the video them call out terrain relative navigation. And we had some cameras on board, and they took on board autonomously, it took images of the surface, and it mapped the features in those images to our map. And as we descended on the parachute, it got a measure of the velocity as it's moving over those features. So it knew where it was, and it knew where it was traveling, velocity-wise, and it found the closest safe zone. And then on board, it did a propulsive maneuver called a divert maneuver to move to that safe zone. And you can see it as it was coming down in the higher resolution on the right here. And you can see it picked that blue spot, which, by the way, after the fact, we determined was mathematically the correct place for it to have chosen. But during the landing itself, we here on the Earth had no control over this. We didn't know which of these blue areas it was going to end up landing in. It's the first time we've sent a probe to Mars where we didn't have a bullseye that we were aiming for. We let the vehicle autonomously determine its own bullseye in flight. And to me, that's remarkable, right? And we do that kind of stuff on the Earth, right? When you're driving around with your phone and your GPS, you're making decisions about traffic and do I go to the right because it's a shorter route or what have you. That's basically what Perseverance did on its own on the way down to Mars. We also carried the first in situ resource utilizations experiment on board Perseverance. We made oxygen on Mars for the first time, right? We made it in a small quantity, and we're making it still today at different intervals as the mission moves forward. But we made oxygen on Mars. And of course, humans need oxygen to breathe. Oxygen is a very useful propellant if you want to move around on the Mars surface or build a rocket that's going to bring people home one day. And so that's an important technology accomplishment as well. And then, of course, we have Ingenuity, the little helicopter that could. Designed to last just a week or two, designed to do a maximum of 5 flights. We just completed our 15th flight, by the way, last week with Ingenuity. And Ingenuity went from being an experiment, like can we fly at all on Mars? Is the atmosphere too thin that we can't get enough rotor speed to get enough lift without going supersonic right at the tips, to actually lift the helicopter and control the helicopter on Mars? It went from that to being an actual science scout, where Ingenuity is flying ahead of the rover and actually acquiring imagery that the rover can use, or the scientists back here on Earth can use to decide where the rover should go next. So we're in this place called Jezero Crater. It's a remarkable scientific vista. It is, if you're a geologist or a planetary scientist, Jezero Crater is your candy store. It's got a little bit of everything. And the scientists are having a field day with this mission. We believe that this is an artist rendering, obviously, over there in the inset, but we believe that that's what Jezero Crater may have looked like a long time ago, 3.5, 4 billion years ago. This is what it looks like today, right? And so what we're trying to do is understand that against this. I mentioned Ingenuity. I just want to talk about it real quick. This is a selfie that the rover took of itself with its partner, its little buddy, Ingenuity. And what's shown in this inset is a view of some of the rocks that Perseverance is exploring right now. The kind of the blurry one is what we see from orbit with our best camera. We have a great telescope looking down on Mars. It's on a spacecraft called Mars Reconnaissance Orbiter, and it sends us almost all the data that you see about the image of the surface of Mars. But look at the view of that same image that we can get from our Scout, Ingenuity, which is flying maybe 12 meters, 10 to 12 meters above the surface. By the way, that's with a COTS camera that was not spaceflight qualified, right? A camera much like the cameras in your cell phone. A little bit different, but not greatly different. Because once again, Ingenuity was a test. It was an experiment. And so we took a lot of risk in the systems of Ingenuity. Now, Perseverance has done some amazing things for itself. And what I really want to focus on, because it's leading me into my next topic, is this rock and these holes. That didn't naturally form, right? I think you can tell that. What that is that rock was sampled. We actually acquired core samples of that rock twice, one in each hole. So we have a hollow drill, basically on the end of the arm of Perseverance, and we can, as we move around, we can sample these rocks, acquire core samples, seal them in metallic tubes that we brought. We brought 43 titanium metallic tubes with us. And as we traverse around Jezero Crater, we're going to collect a good number of these rock samples. And then we're going to place them on the Mars surface, some of them on the Mars surface, keep some of them on the rover. And at some point in the future, which I'll talk about in a minute, we're going to go get those samples. And we're going to bring them back to the Earth. And that will be the first round-trip Mars mission, in my view. It'll be a scientifically driven Mars sample return mission. And that Mars sample return, frankly, has already begun. Perseverance is the beginning of the Mars sample return campaign. So here's that rock, Rocher, that we've sampled. This is an image of one of our two sample tubes that we took on, Sol means day, by the way. A day on Mars is 24.6 Earth hours. So we use a different term than a day. All right, so it's Sol 190 and Sol 196 where we acquired these two samples. This is a close-up view of those samples, and so you can see a little bit of the crystalline structure and a little bit of the composition of these intact samples. Each sample, by the way, is roughly the size of a piece of chalk. That's just something that I thought you'd be interested in. And then we seal the sample tubes themselves for eventual pickup. Now, how will they be picked up? So at the same time, Perseverance, by the way, is going to traverse across the surface probably for the next 5 years, at least. I mean, Curiosity's been going since 2012, and it's still going strong today. Perseverance is an improved version of its older sister, Curiosity. And so while Perseverance is traversing and scientifically selecting just the right samples to bring back to Earth, we here on the Earth are developing the next systems that will fly to Mars, get those samples, and bring them back. And we're doing it not just in the United States, we're doing it across the world in collaboration with our European partners. And so what we're planning is a really grand voyage of discovery that we call Mars Sample Return. And it, as I said, it started with Mars 2020, which is now, kind of up there in the top corner, doing its tube collection of various samples across Mars. It will keep some of those samples on board in case it's still alive when we arrive with these other missions, and it'll place other samples on the ground in case it doesn't make it, in case it has a failure. And we will carry with us on one launch an orbiter with a vehicle designed to come back to the Earth, and on a second launch, another lander. And this other lander will land right near where we place those samples. And off of that lander will come something we call a sample fetch rover, a smaller rover that's being built by the Europeans right now, will go off, gather the samples that are placed on the Mars surface, and bring them back to that lander. That lander will also contain a large missile, basically. It's called the Mars Ascent Vehicle. It's a two-stage rocket, solid propelled rocket. And the samples will be placed either by the sample fetch rover or by Perseverance in the nose cone of this rocket. It'll be sealed again. And then when the time's right, that rocket will launch into Mars orbit, where we will autonomously rendezvous with that orbiter that we sent ahead of time. It'll be the first robotic-to-robotic rendezvous at another planet. Once that rendezvous proceeds, the samples will be transferred into the orbiter, which will leave Mars and come back to Earth. The samples will be in an Earth entry vehicle, which will be positioned to fly through the Earth's atmosphere and down to our surface, and they'll be recovered here on the Earth. An entire round-trip mission to Mars, all robotic. It's going to be happening in this decade. We're going to be launching these missions, both the Earth Return Orbiter and the Sample Retrieval Lander, in this decade. And so Perseverance will meet Mars Sample Return for the first time, these elements of Mars Sample Return, on Mars. And so one of the things that we're doing as we continue to fly or operate the Perseverance mission, and this is a notional view of where Perseverance may go over the next several years. Right now we're in this roundish ellipse called, Jezero Crater Landing Area. We're going to continue to explore there for a year or more, and then eventually we're going to explore outside that. We're going to climb over the crater rim and down towards this other area where there's additional scientific interest. We're going to explore this whole area, which, as you can see, is on the order of 30 square kilometers, right? And we're going to place tubes down on the surface as we go to minimize the risk of a challenge with Perseverance. But I actually think Perseverance is going to be just fine. And we will land somewhere along a place like this where Perseverance has traveled that is also safe for landing, and Perseverance can come back and meet us. And so Perseverance will meet the Mars Ascent Vehicle on the sample retrieval lander in one of these locations that are numbered. There's like 36 of them that we've already proven are safe, both for Perseverance and for the landing of this next system. And this is what that might look like out towards the latter part of this decade. Here we have the sample retrieval lander with the Mars Ascent Vehicle in a horizontal position. And here we have Perseverance that has made it and is coming with some of the samples, and the sample fetch rover designed by the Europeans that has gone to get the samples off the surface and brought that back as well. So once again, while Perseverance is operating on Mars, here on the Earth right now, engineers and scientists across the planet are working on the sample retrieval lander, the Mars Ascent Vehicle, the sample fetch rover, the Earth entry vehicle, shown all the way over here, the Earth Return Orbiter, which is a solar electric propulsion based system so that it can go out and back efficiently. And we're making that all happen in this decade. It's really, for Mars exploration, it's really a marvelous time. So I want to move to just a couple other things real quick, because I don't want you to think that all we do at JPL is Mars. We do a lot more than that. Our next mission to launch, in fact, is not going to Mars. We have a mission launching in August, this next August, and it's called Psyche. And it's a mission to an asteroid named Psyche, which is where the mission gets its name. And the Psyche asteroid is thought to be an iron core that didn't form into a planet. So remember, I told you that the reason we study the planets is to learn more about the Earth. Well, one of the things that scientists would love to know is the history of our own iron core and the dynamo and its evolution over time. Now, we can't send a robotic probe down to the center of the Earth, but we can look at an iron core out in space. And so through telescope observations, Psyche was identified for exploration. And we're sending a robotic spacecraft, solar electric propelled spacecraft, being built in the clean room at JPL right now. This is an image from a couple weeks ago of that spacecraft. This is a mission that we're doing in partnership with Arizona State University and Maxar and a number of other players across the country. Launching in August. To launch from Florida on a Falcon Heavy. In 2024, the U.S. will be sending our next mission to the Jovian system, out towards Jupiter. We won't be studying Jupiter like the Juno spacecraft is doing right now, a mission that was launched more than about a decade ago. But we will be studying Europa. Anybody ever see the movie 2001, A Space Odyssey, right? To Europa? There you go. All these worlds are yours, save Europa, attempt no landing there. Well, we won't be landing. But we will be flying by from a high altitude, and we have a dozen instruments on this spacecraft, and we'll be mapping this world from orbit, much like we map the Earth from Earth orbit. Europa is a fascinating world. It's ice encrusted. The ice has cracks in it and fissures. There are thought to be plumes or geysers of water that go up into space from time to time. The thickness of the ice is one of the unknowns. It's thought to be variable, but anywhere from a few to tens of kilometers thick. And below that ice, we know that there is a deep ocean, a salty ocean. Talk about exploration, right? Let's learn more about the ocean on this world in our own solar system. There are actually half a dozen to a dozen ocean worlds in our own solar system. There are certainly hundreds, if not thousands of more around other planets that are around other stars. The Earth is not the only ocean world out there, right? So one of the ways we can learn more about the Earth and its evolution is to study Europa, an ocean world. And right now in the laboratories at JPL, at the Applied Physics Lab, at Goddard Space Flight Center, and at industry sites around the country, hardware is being produced for this mission. And so this is just a smattering of some of the hardware, some of the instruments, and other hardware that's coming together now. This mission will be launching in 2024 to Europa. Now, after 2024, out into the late part of this decade and early next decade, what's going to happen is still up in the air. And actually, if you're a student here at NC State, this is probably a time frame that you care about, right? This is a time frame where you could make a contribution. The reason I say it's up in the air is because one of the things I love about planetary science or any kind of space science is that the community gets together once a decade and they make a wish list. And it's a prioritized wish list of the things they want to do in that decade. All the planetary scientists provide inputs, they write white papers, they argue amongst themselves about why going here is a better idea than going there, and the scientific discoveries of potentially of one mission over another. And then there's a scientific committee that integrates all that input and comes out with a set of priorities. And that next set of priorities is going to be published by the National Academies in March of 2022. And that report will set the direction for planetary science, in this next decade, going out into the 2030s. Now, there are a number of missions that are vying for position, you might say, in this report. And really, the top missions, what they're vying for is who's first, who's going to go first, and who's going to go second. They're all going to happen because they're that good of missions. And so some of the missions that are being discussed by the decadal survey, I just don't know the dates yet because I don't know the priority, right? But some of the missions include an orbiter to go look at some of the gas giants like Uranus or Neptune. You know, the gas giants are the sentinels of our solar system. They're thought to be, well, they are remnants that preserve the history of the very early solar system. So if we want to know how Earth formed in our own solar system, studying the giant planets is the way to do that. And so an orbiter to either Uranus or Neptune, perhaps with a probe to sample the atmosphere and fly down through the gas giants themselves, is something that's on the docket, something that's being considered. Another thing that's being considered is to follow up on some of the orbital observations by going to the surface on one of the half dozen of ocean worlds in our own solar system. So this could be Europa, Enceladus, Ganymede. They tend to be the moons of the giant planets. They tend to be, by the way, these moons are roughly the size of the Earth. They're not small moons because everything in the giant planet system is giant. And so, for instance, if we were to go to Europa, we would follow up on the Europa Clipper orbital observations by actually landing on that ice-encrusted world and digging into that surface, doing some astrobiology science, looking for signs of life or organics on the surface of Europa, or Enceladus, where there are plumes of water blasting into space from the South Pole nearly continuously. So I wanted to talk about these not because I know when they're going to happen, but I do know they're going to happen. And I do know that students from NC State or universities around the country have the opportunity, if you choose, to contribute to these kinds of missions. And also to be a part of some of the most amazing teams that I've ever had the honor of being associated with. So the people that make this happen, I mean, to be honest, it's not me, okay? I get to stand here and talk to you today, but it's the thousands of people, engineers and scientists, that are working from home or working part-time on the lab or working in their university environment all across the country that are working together, collaborating to make these missions come together. It takes scientists, it takes engineers, it takes all kinds of people to do these kinds of things. And this is, by the way, just a smattering of some of the people that I work with that have made Perseverance possible. But this is the way we're doing all of our systems right now in this time frame. We do go to the lab, of course, to build hardware and to test hardware, but there's a lot of remote work, and it actually, in some ways, the remote work has enabled people from across the country to do things that they wouldn't have otherwise done because, you know, you had to go on travel or something like that. The last point I want to make before I take some questions is that we've been thinking long and hard about what is JPL's role in our world. And of course, JPL's role is to do the first of a kind, one of a kind missions. That's always been our culture. That's what JPL is known for. We are the premier space science organization, not just in the United States, but in the world. But you know, focusing on the what you do is not who you are. And it's certainly not who you want to be or who you want to inspire. And so at JPL, we've set a goal that we want to inspire the world. We don't want to inspire just the people who we happen to look like now. We want to inspire the world to join us because we know through our own experience that diverse teams are the best teams. And so not only can we achieve these fantastic missions, but you know what? We can be a leader in STEM. We can lead others to a more diverse and inclusive and even equitable future. And it's something that the lab is very serious about. So you will be hearing more about this over time because JPL is focused on this and rolling out plans, diversity, equity, and inclusion plans that engage all of our partners across the country. Whether it's a university partner or industry partner, JPL can drive change, and we intend to. So with that, I want to say thank you for your time. I really appreciate, once again, the opportunity to be here and speak with you, and I'm happy to take any questions you might have. Thank you very much.
Thank you, Bobby. We have time for a couple of questions. Venkat? We'll have to repeat the question. Repeat it?
My question is, you talked about entry, descent, and landing.
Yeah.
I wonder if you can elaborate a bit on the challenges and innovations that you're looking for EDO technologies when you go for other exploration.
Yeah, well, so I could give you a whole seminar on entry, descent, and landing technologies, and I would love to do that sometime. But so in EDL, obviously it's a critical risk area, right? It's a binary result. You're either going to be successful, and it's going to be the best day of your life, or you're not going to be successful, and it's going to be horrible, right? There's no in between. There are thousands of things that all have to go just right for an EDL success. And so we focus very much on making sure all of our systems, perform. But from a technology standpoint, we're focused on a number of things. Landing more accurately, as you saw in Perseverance. I could show you another plot that shows, from Viking's landing site to Mars Pathfinder, to the MER rovers, down to the pinpoint landing, basically, that we just did on Perseverance. It's amazing the technology advancement that's come along in just the last 10 or 20 years. That's been done through going from just poor navigation to better navigation, to flying lifting vehicles and guiding those vehicles through the atmosphere with an active guidance system like we did on both Curiosity and Perseverance, to adding systems like terrain relative navigation that get us down to being able to land within a football field, right? We also want to take more mass to the surface. Landing big, heavy things on Mars is not easy, okay? And if you think about the sequence of the missions that I just ran through, Mars Pathfinder landed a rover that was like the size of a little baby, right? Perseverance and Curiosity are the size of a car, right? If we're going to one day land humans on Mars, we need to land a 2-story house. And we need to land that 2-story house right next to other 2-story houses that have been pre-positioned and, powered up and fueled and, have food and other necessities growing in them. So landing more mass is certainly something we're looking at. Now, if you go beyond Mars, there are all kinds of other technologies. There's heat shield technologies, for instance, at Venus or at the giant planets where the entry velocities are really high. There's a lot of heat shield technology that's being worked on. At a number of destinations, we need advancements in our supersonic decelerators, so parachutes or other forms of deceleration supersonically. And the list goes on, but that's just a subset for you. There's a lot of work still to be done in that field, and if you're interested, places like NASA Langley or Ames or JPL, Johnson Space Center, are all great places that would be interested in working with you on that or in that area. Yes, ma'am.
I have a comment and a question. So comment is, everything you said about JPL is really true. I'm one of the interns who worked on Perseverance. I'm from 2000.
Good for you.
JPL since 2017. I know my heart skipped a beat when that landed. I worked on Mars sample return. And the question is, there are technologies that you send to Mars. They're all started as low TRL and high risk. What is the trajectory for them to get them to the technology readiness level for a space mission? Say I have a very revolutionary idea, and obviously it's high risk and low TRL, and I need to get it to TRL 10 in order for me to send it to Mars. So how many years and how many people you need to sell it to? What is the trajectory of that?
Okay, so I'm supposed to repeat the question. So the question has to do with technology advancement and how do we advance ideas from, revolutionary ideas, from concept all the way to flight. First of all, thank you for your efforts at JPL. Appreciate that. So there's not like a straightforward process that's written down that you just follow step 1, follow step 2, follow step 3, and then all of a sudden your technology is flying in a space mission. But we do have the technology readiness scale that you referred to. And so very often there will be early stage ideas, very low technology readiness level ideas, and they get seed funding. And they're really just ideas, and the people working on them, of course, think that they're ready to fly right away, but they're not. They're brilliant ideas, and they're gonna make a difference on a mission one day. And so they go kind of from analysis space, if you will, and design space into testing, usually ground-based testing. Oftentimes they'll be flight tested, maybe on a sounding rocket, dropped out of a helicopter, depends a little bit what the technology is. Maybe they'll be in a 0G flight if they have to get tested in space. They could be launched to the space station and fly in low Earth orbit. And then once they're proven in a relevant environment, then they're ready to be infused in a mission. And so, for example, I could take the TRN, the technology, the terrain relative navigation system that we just flew on Perseverance. That's something that we've been doing on the Earth for many decades, frankly. It's something that had been proposed that we would do on Mars. I can imagine that, I'm pretty sure that I wrote a paper at least 20 years ago that talked about our ability to one day do this. But just because I wrote a paper didn't mean it was ready to go. And so in that time, TRN went through all those steps. They went through all kinds of simulation analysis. They actually proved themselves flying over simulated Mars terrain from a helicopter that was dropping as fast as Perseverance is dropping to the surface in that video I showed you during the landing. And then they needed a scientific pull also. And so it wasn't necessary to do TRN on Curiosity for the science that we wanted to do, but it was necessary for the Perseverance science. And so the technology was mature. There was a scientific reason to do it, and so it made it onto the flight, as an example. And there are a number of things like that have gone that way. Now, in my field in entry, descent, and landing, one of the things that I've enjoyed the most is working with students. And what I do is I work with them at Georgia Tech or at CU Boulder and now at Caltech in my lab. And what we're working on are those technologies, those ideas about the future of entry, descent, and landing. None of my students' work, when it's published in a journal article or in a PhD dissertation, none of that is ready for flight that day. But those same students go to work at JPL, or they go to work at Langley or Ames. And guess what? Within 5 or 10 years, they take that work and they fly it on a mission because they know all about it. They're up the learning curve, and then they can infuse that technology into the mission. And so for me, at least, it's been remarkable to get to work with these students and watch that TRL progression through their eyes. You know, if you're a student out there, what you're doing in university today, it may not fly on a space mission today, but it will fly. If it's a good idea, it will fly in your lifetime, and you can be a part of that. And it's, you know, there's nothing better than that. Thank you for your question. Yeah, one more. Bob?
Using a rotorcraft on Mars has some interesting possibilities. And you mentioned it was very low pressure atmosphere. Can you tell us more details about how the rotor was designed?
Yeah.
To enable that kind of a rotorcraft to work? Also, somewhat related, do you consider a wing flapper configuration?
I know that you have. You're right, you're right. Okay, so questions about Ingenuity and the rotor design and its operation in the very low pressure environment on Mars. And thank you for that question. I love talking about Ingenuity because it's such a marvelous success story, right? It was totally an experiment. It was something that was added very late to Perseverance. It's relatively low cost. And it's just been remarkable, and it's proven itself not just from a technology standpoint, but it's actually proven itself as a science scout. So now all the scientists are rooting for it. And before I answer your question directly, I will say we're now working on future rotorcraft that will do much more significant flying on Mars and elsewhere in the solar system than Ingenuity in terms of duration, in terms of the payload that it's able to carry, you know, scientifically and that sort of thing. So getting to Ingenuity itself, it's a remarkable system. It's, you know, very, very small, very lightweight. But the challenge, of course, is, you know, even for a few kilograms, is getting that few kilograms up in the very thin Mars atmosphere, the very low density of Mars. Mars, on the surface of Mars, roughly speaking, you know, the atmospheric conditions are equivalent to about 100,000 feet here on the Earth. And as you know, there are no airplanes flying in a stable state at 100,000 feet here on the Earth. And so what we had to do is not just build a lightweight drone that could survive the space environment, launch through radiation in space, the landing, and the very cold environment on Mars, but we had to design a system that could fly and operate, you know, like a helicopter. And so for us, what that translated into is being able to spin the rotors at about 5 to 6 times. We've actually increased it as the density has been dropping on Mars, 5 to 8 times what a typical drone rotor spins at. So we're spinning right now at about 2,800 RPM, okay? And that, you know, that rotation rate, without getting too technical, that rotation rate translates directly into the tip speed of the rotor, or the speed of the rotor. And so we had to design an airfoil section, you know, conducive to that density, velocity combination. And that's something that we did in partnership actually with AeroVironment, which is a small company in Simi Valley that's done a number of, you know, one-of-a-kind drones that have flown here on the Earth. So that system, you know, we designed it through analysis. We built it up. We tested it in a pump-down vacuum chamber. And we actually had challenges with control of that system that we had to overcome. You know, it would lift off, but then it would go unstable very quickly. And so once all those challenges were proven here on the Earth, we took it to Mars and proved it out there as well. But there's all kinds of, you know, composite materials and advanced aerodynamic design in that system. The next rotorcraft that NASA is building will actually fly on Titan through the Dragonfly mission. And the Titan atmosphere is basically the opposite of the Mars atmosphere with Earth in the middle. So it's a much easier place to fly. But they'll be able to carry a much more, as a result, a much more significant scientific suite of instruments. Okay? Thank you.
All right, thank you, Bobby. This is a token for appreciation
Oh.
for, I think.
Thank you.
If you come this
Oh.
way, we can get a picture of that, just so that you can remember that you did give this lecture. I will try.
Sure. You want the,
First one.
this one?
That one.
Thank you. Thank you all very much. I appreciate your attendance, and I appreciate all this university has done for all of us at NASA and in planetary science. Thank you very much.